Hello, welcome back, my wonderful Gen Chem class. How are you? I am really excited. This is our second video in our thermochemistry series. We've got one more term to define, and I kind of want to draw at least another energy diagram. But then after that, I've got a couple problems that I want to use that table I just showed you in the last video. So hit pause if you need to, but you're going to need your calculator for this one. We are going to do some calculating after this first example. So I'm so excited. Our thermochemistry is still our topic. We're still going to look at our change in internal energy due to that heat flow. Okay, I love it. And whenever we're looking at the change in internal energy due to heat flow, this is our enthalpy. Awesome. So I wanted to sass it up just a little bit and show you what a normal question would read like. And what we're calculating is the enthalpy of formation. That is a good place for us to start. So I want to build on what you just learned in your last unit. So this is so much fun. Shut the front door. You know where I'm headed. I'm about to give you some words and have you draw the equation, figure out what the equation is, slap on those yoga pants and light a candle because we need to find our balance. I mean, we're going to do all of that and all in one example. So let's take a look at what a normal test question would look like for this. And then we're going to add just a little bit more vocab to it. So we're going to look at our energy diagram for the combination reaction to form. Okay, what does that mean? That means it's a formation reaction. And we're going to form gaseous carbon dioxide. Okay, how in the Sam heck are we going to write that? Well, if we're forming carbon dioxide, that means it's on this side, and it's going to be in our gas form. And then if it's a formation reaction, you just did this on the test you're taking now. How do you know what it's coming from? Well, it's a formation reaction. It's coming from its elements. Okay, and then we can use whatever's on the table for these. So I'm going to mark this one as a little bit of a question mark because some tables have two versions, and I'm going to teach you how to know which one you're going to write. Okay, then we pause for a second and we find our balance. And we just got lucky. This one seems to already be balanced. And we already know that these are our reactants. That's kind of redundant, right? And these are our products. And then let's go ahead and look at our change in internal energy. Okay, well, what does that mean? That is our energy diagram. That change in internal energy, we can't actually calculate the internal energy. We don't know what it is, but we do know that we can stick a thermometer in this reaction. We can use an equation called specific heat, and we can get that heat flow and that enthalpy. So what do we need to reinvent the wheel for this one? Do you feel like this reaction has probably been done in the last 200 years? Absolutely. So this reaction has been done. So let's flip for a second to our table, and let's figure out what that enthalpy is so we can draw a proper energy diagram. All right, here's our PowerPoint for our thermochemistry table. This is the first one that we're going to use. We've got two tables. This is the first one. All right, so let's look for carbon dioxide. Is it on here? It is, and in fact, it's in that gaseous form. So negative 393.5. Okay, let's go write that down. Let's see if I can remember that. 393.5. I'm going to write it right here. I like to get in a habit of writing these kind of in a little table. In fact, I'm just going to make a little table right there. Okay, so minus 393.5. Awesome. So what does that mean? We learned in the last video what that negative means. That means our heat is going to flow out. You are flowing from your system to your surroundings. Okay. So is that exothermic or endothermic? That is exothermic. That means we're going down in our energy diagram. If we start up here with carbon and oxygen, and we release energy, then we have to go down in internal energy. You just gave that energy away to your surroundings, so that internal energy is now lower. And it's lower by 393.5 kilojoules. Okay, I love it. And then we commented in our last video, well, hang on a second, this is 2 for the price of 1. This is the energy tied up in those bonds. This is the energy that you will get out when you make those bonds. And the same holds true of that energy flow. If you want to break those bonds, you have to put that much energy in. So our table works both ways. It's up to you to know the direction. Okay, so that's what that number tells us on the table. If it's negative on this side and it's exothermic, it's going to be positive on this side. We're doing the exact opposite. So that's the reason these reactions have been studied 6 ways to Sunday, because holy crap, what did we just figure out? We just figured out the energy in those bonds in CO2. We know how much energy you're going to get when you form carbon dioxide. We know how much energy it takes to break the bonds of carbon dioxide. This is phenomenally powerful. I want to take one step deeper, and then we're just going to calculate. And that one step deeper is something called a state function. Okay, I want to take a little bit of a sidebar and go back to our energy diagram with our water. So let's say we put our beaker of water on our stove, and we know that we put in enough heat flow to get that water boiling. So we went from room temperature to boil. Okay, and then we let it sit. And of course, we could cool back to room temperature. And wouldn't that heat flow just be the same, but opposite? Yeah. Okay, that's what we're learning. So this would be our endothermic. This would be our exothermic. Okay, now let's get deep. Let's Dr. Phil this for a little while. Let's get deep into our feelings. What if I were to ask you, does it matter if that beaker right here, the one that we let cool to room temperature, what if that beaker of water was actually ice cubes last night? And overnight, I let it warm up to room temperature. And then what if last night it was boiling and I let it cool overnight to room temperature? Would it matter for these amounts of heat flow? If we are going between room temperature and boiling, does it matter how we achieve that room temperature? Did it matter that 10 minutes ago it was not at room temperature? If it was above or below room temperature? This is such a deep concept, but it actually doesn't matter. That's what a state function means. What my internal energy is based on the state it's in right now, not how it got there. So often, something that's a state function is called path independent. All right, just like many of us, right? We are path independent. It doesn't matter how that beaker of water got to room temperature before your experiment. It only matters that it's at room temperature right now when you started the experiment. Your internal energy is based on that temperature right now before your experiment. It's not based on what that temperature was 2 hours ago. It's based on the state it's in right now. So a state function, energy is a state function. That internal energy matters the state that it's in, not how it got there. So is enthalpy. Okay, so you'll see this in Chem 2. Because it's a state function, we can do all kinds of things. So in other words, in a chemical reaction, what if I mix C and O and I stick a thermometer in it and I do end up with CO2, but in the middle, I make carbon monoxide first, and then my carbon monoxide turns into CO2. Does that matter? No. It only matters that overall process, and that we started here and we ended here. It doesn't matter the path it takes to get there. So that's pretty deep. That's our last deep comment. The rest of this, let's just calculate, calculate, calculate. Okay, so if we're looking at this whole process and we actually want to do some math, well, let me ask you a question. Since I now know exactly how much energy is tied up in this CO2, what happens if I turn around and do a reaction with CO2? So whether I use CO2 as a reactant or I make CO2 as a product, won't the energy be the same? The energy is absolutely going to be the same. That's what's so important about that state function. I can use that number for CO2, whether it's a reactant or a product, and whether it's in any kind of reaction. It doesn't have to be a formation reaction. What? Our world just got so much bigger. This is so awesome. So what we're literally comparing then, let's go back to our table for a second. What we're saying is, if we go back to our table, what's genius about a formation reaction is let's compare, hang on, let's write out carbon. Okay, oh crap, there's 2 carbons. How do I know which one to pick? You pick the one that's 0. Let's pick then our oxygen. Where's the oxygen? 0. All of our elemental forms are 0. Okay, in real life, are they 0? Heck no. Is the internal energy of oxygen 0? No, but we haven't bonded yet. So in thermo, you need a place to start. So all of our elemental forms have been set to 0. So if we compare our product side to our reactant side, this is our answer. The other 2 are 0. All right, so let's get just a little bit deeper. These are going to be so much fun. These look impressive to your friends, so go bust them out at a party. Oh, wait, you're social distancing. Never mind. An online party, Zoom party. Okay, so bust these out because they look really impressive, but really the math is way better than anything you've done before. In this class, it's easier. Okay, so let me show you. Let's take a reaction. This time, let's make CO2. I'm going to start by writing out what I already know. That table that has that information for bonds is going to tell me how much energy I'm either going to gain or lose when I make or break bonds of CO2. So what did we just learn in the last example? What was that number for CO2? It was minus 393.5. Okay, now CO2 is on the product side, so I'm going to write 393.2 kilojoules. That means I am making carbon dioxide. It doesn't matter how, it's a state function. Anytime you make CO2, that is your state. It doesn't matter how you got there. So you can write that. Well, and we just learned, hold on a second, that anything in its elemental form is going to be 0. So now this reaction is more complicated, but can't we do the same thing for methane and water? Well, shut up. Yes, we can. Let's go grab our table. What is CO4? Okay, minus 74.9. Remember that. Okay, minus 74.9. Okay, all of these are kilojoules per mole. I'm just running out of space, so let's have that. Okay, and then what about water? Let's find water. Where's water? Don't tell me to pick the only table in America that doesn't have water. Here it is. Gas or liquid, which one are you going to pick? I'm going to pick gas. I would normally tell you which one. If I don't tell you, it doesn't matter. But in this case, since we're lighting something on fire, you're going to produce a gas. You're going to produce steam. So 241.8. 241.8. Let's write that down. Again, that is kilojoules per mole. Okay. Just hold on a second. Obviously, I'm not in my yoga pants and lit a candle right now because I did not find my balance. So let's stop and regroup for a second, and we need to balance this reaction. We can't go forward. We haven't balanced this reaction. So let's take a second to balance. All right, I've got 1 carbon, 4 hydrogens. Let's put a 2 here. Okay, there's 4 hydrogens. And then now I've got 4 oxygens. Let's put a 2 there. How's that? Okay, why do we give a crap about our balanced reaction? Because remember, this is kilojoules per mole. So that means that my methane is only 1 mole. My oxygen is 2 moles. My carbon dioxide is just 1 mole. But my water is 2 moles. I like to just write that in right away. Write out your data, write in your moles. Most common mistake on this next test is to forget your moles and balance your reaction. Now it becomes a math problem. We are going to compare, and we are going to take our products minus our reactants. So we're literally going to compare, okay, what has to go in versus what's coming out. So obviously you've got to put some energy in and get some energy out when you're doing a reaction. So on this side, CH4, this number is only if we make CH4. We're not making it, we're using it. So our sign is wrong. So I don't mess with my sign. What I prefer to do is, wait a second, I gotta use a different, okay. What I prefer to do is to do products minus reactants. That way you keep your signs the same and you don't have to confuse yourself. So let me show you what I mean. We're gonna compare if we have to put energy in over here to the energy we're gonna get out over here. That's it. So the first thing is we do not have a formation anymore. We now are using a full reaction. So RXN is our abbreviation for a reaction. And we are going to do one massive sum. And we are going to sum our products. Remember, that's the energy that we're going to get out minus the reaction, the reagents, reactants. Let's just try 5 words and see if we can get it right. Our reactants are the energy that we have to put in. So we're going to compare them and see what this overall process is going to give us. So bust out your calendar. Oh my God, y'all. I guess I'm brain fried. Bust out your calculator. I don't think your calendar is going to help you on this one. And let's draw something that looks really fancy, but really isn't that bad. Let's take our products and let's do one big sum. Okay, that is my CO2. So that is my minus 393.2 kilojoules. And now I'm going to take care of my moles. Okay, in this case, it's only 1 mole. And then I'm going to add my water. Did I really write 24.8? Isn't that 241.8? That seems a little bit better. Let's multiply that by our moles. That is times 2. Okay, so we need the sum of all of our products. And then we're going to subtract. So this is where you want to hit pause in a second and actually try this on your calculator, because the tricky part is just your parentheses. How are you going to enter that in? So then let's subtract our reactants. What do we have? We have our CH4. And we actually just have 1 mole there. And then we've got 2 moles of our oxygen. So we got a little lucky, that's just 0. All right, so let's take a second, plug this in on your calculator, and let's see if we're matching. And that is going to give us the overall full reaction. So really, this looks really sassy, but all you're doing is grabbing a table and adding and subtracting. I kind of love it. And of course, finding your balance. All right, so I'm going to take a second to actually plug this in on my calculator as well. All right, and then I'm going to subtract. I just did the first part. And just for funsies, I'm going to write what I got for the first part just in case you're doing this stepwise. And then I'm going to subtract that negative 74.9. And then now overall, that means I'm getting a negative 801.9 kilojoules. Okay, I love it. So double check that. Do that on your calculator. Let's see if we're matching. And now, what does this mean? This entire reaction, is it endothermic or exothermic? Look at that negative. That's why we don't jack with signs. You do products minus reactants and keep your signs the same as what's on the table. Okay, we ended up with a negative, so that means this is exothermic. So if you do this reaction in your hand, and please don't, because of course it's on fire. So don't do this reaction in your hand. But if you did, you would burn it. Okay. So this is a nice exothermic. And you would literally, if you did this reaction as is, 1 mole of methane, 2 moles of oxygen, 1 mole of carbon dioxide, 2 moles of hydrogen, you would make 800 kilojoules of energy. I'm sorry, you didn't make energy, you didn't create it. Your energy would be transferred. You would release that much energy. Isn't that maybe why you have a methane stove, or a natural gas is methane? So if you've got natural gas as stoves or grills or anything like that, doesn't that make sense? You actually need an exothermic reaction or you're not cooking squat. Nobody goes out to grill and hopes that their food gets colder and not hotter. So otherwise, that's why this is productive. All right, let's turn around and just do one more of these. These are so much fun. You've got some in your homework to practice. In fact, I think you probably have very similar ones to these. All right, so what's the first thing we're going to do? Find our balance. Put on your yoga pants, light your candle. Let's do this. All right, I've got 2 nitrogens, so I'm going to try that. Let me write that a little smaller, okay? That means I've got 6 hydrogens, okay? And then 2 oxygens, son of a motherless goat. I have 3 over here. So in theory, that would be 3 halves. So I'm going to go ahead and multiply this whole thing by 2 and end up then with 4 ammonias, 3 oxygens, 2 nitrogens, and holy cow, 6 waters. Okay, I love it. Are we balanced? 4 nitrogens, 12 hydrogens, 6 oxygens, 6 oxygens. Done. Okay, we're nice and balanced. Then the second thing I like to do is start reading the table. We've got to write out what each one of these things is. Actually, let me give myself some space because we got a little cramped on that last one. So I'm going to start over here. Let's write out what each one of those is. So let's find, wait, I know the easy one. Okay, 0. Ooh, 0. All right, let's find ammonia. Wait, wasn't that in our last video? It was. I can't remember that though. So I'm going to go grab that on my table. Okay, what was ammonia? 95 or 45.9. Okay, 45.9. Again, these are kilojoules per mole. I'm just going to save some space there. And then water was in our last example. What did we use for water? 241.8. Okay, I love it. So don't forget your moles. What I like to do is write it in right with my data. I'm going to go right here and put in the 4. Just for funsies, I'll put in the 3 and the 2. And then right here, 6. Don't forget your moles. It's the most common mistake on this unit is to forget your moles. Now let's do one massive summation. And let's do our products minus our reactants. Again, we're just comparing the energy on both sides. So let's take our products, and I'll probably drop the zeros this time. Okay, so let's take the products. I've got a minus 241.8, but I have 6 of them. Minus reactants, I've got 4 of those ammonias. Okay, and now bust out your calculator. Let's do that math. Let's see. I've got a negative 241.8 times 6 minus our negative 45.1 times 4. Okay. I am getting a negative 1270.4. Okay, I love it. That would be in kilojoules. Okay, is this reaction exothermic? Yes, absolutely. That is exothermic. So that whole process, again, if you light ammonia on fire, you're going to burn your hands. So please don't do it. Okay. All right, what do you think of this process? If you can remember to read your table, your formation reactions, and then take products minus reactants, you're in business. All right, so that's our first set of problems. Now, how are they going to be worded? They are going to be worded in order for you to use your thermochemical table. Now, that's the table we've been looking at. Okay, that is our thermochemical table in the homeworks and things from me, because I'm also going to turn right around in our next video and do these exact same examples, but I'm going to solve them using a different table. So go ahead and do the homework on these and practice them. These are actually really fun. Like I said, they look super impressive, but really if you can read a table and add and subtract, you're in business. So they look really pretty impressive. Just let your friends think you're super smart because you are super smart.